let's take a look at rotational motion. Now we've been looking at circular motion, and that's been where you look at the acceleration towards the center of the circle and the forces that actually cause something to move in a circle. In rotational motion, we're actually focusing on the movement of the object. So if you had like a CD, okay, and you put it in a CD player, what it does is it actually spins in a circle, and it spins fairly quickly. Okay. Now, yeah, at this point on the outside has got some centripetal acceleration, and I'm going to call that AC towards the center, but it's also traveling through a distance, and it's traveling around a circle. And this point right here, a little bit further in, it's traveling around a circle too, but that's a different, smaller circle, right? Now, that means every point on here has a uniform velocity, but every point on here has a different uniform velocity. So there's not a constant velocity through this whole distance. So the way we talk about this is, instead of talking about a change in x over time, we talk about a change in angle over time, change in theta over t. And so really we're talking about revolutions. Okay? We're not talking about distance, we're talking about revolutions. And this is what's called angular motion. Okay? So instead of looking at it as a distance that it travels, and a distance, a delta x, that is translational or linear motion. Okay? Now we're looking at it in terms of what angle it rotates through. Okay? So in angular motion, there's a whole bunch of different ways to talk about this. Right? You can talk about a circle in terms of degrees. You have 360 degrees in a circle. 360 degrees equals 1 revolution. But that's not the handiest method for actually doing that. Okay? Instead, we like to use this unit called the radian. I say unit. Now, a radian has no dimension because it's a ratio of lengths. Okay? Basically, the radian is defined as saying if this is a circle with radius r, then we know that the circumference is equal to 2 pi times the radius. Okay, and so we're going to call this radian as actually how many times the radius goes around the circle. What's handy about the radian is it's already the ratio of arc length s, okay, or L or x, whatever you want it to be, to theta. Okay, so what we can say is r times theta is equal to s. Okay, now s is really the distance that this circle would rotate through if you were rolling a wheel or something down the ground. So what we just said was, we said if I want to convert a rotational motion, I just need what angle it rolled through, theta, and the radius, and I can get the change in position of the object. Okay, and so theta is what we use to denote rotational motion. And so let me show you something. Okay, delta theta, that's a change in angle, is sort of the equivalent in the linear. Okay, so let me title this. Okay, we have rotational quantities and we have linear quantities. Okay, and in my rotational side, everything's measured in radians per second, or degrees per second, or revolutions per second, or minute, or whatever. And in translational side, we're measuring things in terms of meters per second, meters per second squared, whatever you've got, distance times speed over here. So rotational, what we talk about is we talk about the angle through which something rolls, delta theta. On the translational side, we talk about the distance through which something moves, delta x or delta y. On the rotational side, then, we're going to be talking in radians. Okay, so you can also use degrees or revolutions. The translational side, we're generally talking about meters. Okay, now that's not the only thing that's going on, right? If you put a CD in a computer or a CD player, it starts out rotating, but it starts fairly slow, and it has to accelerate. Now, if it's moving at a constant speed, then the acceleration is towards the center. But if it's also speeding up and getting faster and faster as it turns in circles, then there's an acceleration around the circle. Okay, and that's called an annular acceleration. And I guess I'm getting a step ahead of myself, because okay, what sometimes we're interested in is how fast something spins, how fast something moves. Okay, right? Delta x over t is equal to velocity. Similarly, delta theta over t is equal to angular velocity. Okay, that's an omega. It looks like a w, but it's an omega. Delta x over t is v. Delta theta over t is omega. Delta x over t is velocity. And of course this is measured in meters per second. This is measured in radians per second. Okay, you can also measure it in revolutions per second or in degrees per second or whatever. Okay, and then we have, okay, so that's velocity. Translational, we have the change in velocity over time, which is acceleration. Okay, and that's measured in meters per second squared. We have that same quantity over here on the rotational side. The change in velocity, angular velocity over time, is actually angular acceleration, which is radians per second per second. Okay, so we have similar quantities in both. It's just that translational talks about a distance through which something moves. So like if I roll a tire along the ground, okay, then the distance this tire moves as it rolls from here to here, that's the translational motion. But the path that a piece on the tire actually takes, or how fast the tire spins, that's the rotational kind of thing. Okay, and there is a relationship, right? Because a bigger tire doesn't take as many revolutions to roll this same distance. And so as long as you're measuring angle in radians, if theta is in radians, then the relationship is really easy. Okay, delta theta times the radius, delta theta times the radius is equal to delta x, and delta theta over time then is equal to omega. Okay, and so if I multiply both sides of that by the radius, then I'm switching into linear again. So what we take is omega times r is equal to v. And finally, there's this other one, alpha, which is angular velocity times r equals a. Now, this acceleration is linear acceleration. It's not centripetal acceleration. And so what I want you to think about on that is, like I was talking earlier, I said, if you take something and you start spinning it faster and faster and faster, if you consider just this point, okay, at one point in time it's got a velocity here of, say, 2 meters per second. Okay, a couple seconds later, or a little bit later, maybe it's moving at 3 meters per second. Now, yes, there is some centripetal acceleration this way. It's not uniform anymore, so we don't know quite how to deal with that. But there is also some acceleration this way, and that's what I'm talking about. And so sometimes this is referred to as tangential, a tangential, and that's alpha times r. Okay, and it's the translational part of that. So if this was rolling across the ground, this would be the rate of its acceleration. Okay, so there's a few problems I want you guys to look at today. But it's basically going back and forth between linear and translational things and figuring out how much a revolution is and kind of getting familiar with radians.